This is the last section for Calculus 1 here in Summer Session B. So in Section 5.5, the indefinite integral and the substitution method. Essentially, all of Calc 2, or not all, a vast majority of Calc 2 is different integration techniques. So a lot of times you can look at a function inside of an integral and you can say, oh, I know the antiderivative for that, whether that's using a power rule or it's a trig function that I recognize, et cetera, et cetera. As the functions inside of an integral become more complicated, we need some techniques. And the very first technique is called the substitution method. It's very typical that this is done at the end of Calc 1, and then you review fundamental theorem of calculus, and as you start off Calc 2 and doing some substitution techniques like this before you move into new material. So this is the last thing we're going to cover here in Calc 1. Most people find this interesting and probably fairly easy to do once you get the idea. So essentially, the substitution rule is sort of reversing the chain rule. Remember, when I take the integral of a function, and by the way, I'm just going to do indefinite integrals right now, so I'm not going to worry about using the fundamental theorem. I just want to know what's an antiderivative for this, and maybe if I want to know all antiderivatives, I just add my plus c, right? So if I see that I have a derivative of something inside of there that is a chain rule type derivative, then the substitution technique says, well, let's let u equal g of x. So I'm going to let u equal this g of x. So then this becomes f of u. And then du is g prime of x dx. So this g prime of x dx becomes du. What have I done? I've changed the more complicated looking integral in terms of x into a simpler integral in terms of u that I should be able to evaluate using power rules or definitions of trig functions or derivatives of trig functions, antiderivatives, etc. So that's the idea. So let's just go through. I'm going to break up example 86. I've done 8 parts to this example. I'll call it all one example, so I'll break it up into 2 different parts. I'll do A, B, C, and D in this video, and I'll do E, F, G, and H in the next video. So example 86, we just want to evaluate the following indefinite integrals. So part A says this one is going to jump out at us, I hope, pretty easily, but I have the integral of x cubed plus x to the 5th power times 3x squared plus 1 dx. So when you're doing something like this, and you may not recognize that that's a derivative of something using a chain rule, but you think about, I want to let u go be the function that's inside of another function. So notice that I have this function, x cubed plus x, but then that is all raised to the 5th power. So I think of my x cubed plus x as my inside function. So that's what I want to let u be. Let u equal x cubed plus x. And then don't worry about what you have over there. Just go ahead and take its derivative. Remember, this is a differential. So I could write this as du dx equals, but I'm just going to write it as du equals the derivative times dx. So du equals 3x squared plus 1 dx. And then I go back to my integral and see if my substitution method worked or not. So remember, I let u be this guy, so that's u to the 5th, and then lo and behold, there it is. 3x squared plus 1 dx actually just becomes du. So this becomes the integral of u to the 5th du. Now it's a very simple integral because u is now my variable of integration, and I just have a power rule. So I add 1 to that power and divide by that same number, so u to the 6th over 6 plus c. And then that is not done, though, because my original integral was in terms of x. So I plug back in what u was, which is x cubed plus x to the 6th power over 6 plus c. And that's the answer to the integral. All right. Similarly, going through the next part of this example, part B, we have the square root of 2x plus 1. So I don't know that off the top of my head by looking at it. So I say to myself, can I use the substitution method? Is there a function that's inside of another function? And I see that this function, 2x plus 1, is inside the square root function. So I'm going to let u be the inside function, 2x plus 1. So du equals 2 dx. So then what I did is I just took these 2 pieces, u and du, and I come back and see if I can plug in. So notice that this is u to the 1/2 power, so that's good. But then all I had left was dx. But I ended up with du being 2 dx. So then if I just divide both sides by 2, I see that dx is actually du over 2. So I put in du over 2. And I'm saying, oh, that's no big deal because over 2, that just means a constant. So I can pull out a 1/2. And then I have the integral of u to the 1/2 du. So it's again, it's a simple integral. My variable of integration is u. So I just use a power rule again. So I add 1 to 1/2, and I get 3/2. Divide by 3/2, same thing as multiplying by 2/3. Remember, I left my 1/2 in front, plus c. So this actually is 1/3 u to the 3/2 plus c. And then I'm not done until I stick back in what u was in terms of x. So it's 1/3 quantity 2x plus 1 raised to the 3/2 power plus c. That's my final answer to part B. Okay, similarly in part C, I'm looking for a function that is inside of another function. I see that this quantity 5x plus 1 is the argument of the secant squared function. So my inside function would be 5x plus 1. So I'm going to let u equal 5x plus 1. Then I'm going to take du. Du is 5dx. Then I'm going to come back over and see if my substitution has worked. So I have secant squared of u, so that part's good. I'm left with 5 times dx. Oh, perfect, that's du. So this becomes secant squared of u du, and again, that's a trig function I should recognize. What function, if I take its derivative, gives me secant squared of u? That would be tangent of u. Don't forget to add your plus c. All right, so the bottom line is I now need to plug u back in to be all done. So my answer is in terms of x, I get tangent of 5x plus 1 plus c. Okay, similarly, part D, I look for a function inside of another function. I see that this 7 theta plus 3 is inside of the cosine function, so I'm going to let u equal 7 theta plus 3. So now my variable is theta. I'm just switching it up on u a little bit, because remember, this is just a dummy variable over here, and u is another dummy variable. So I can take the derivative of u with respect to theta, or du is 7 d theta. So then I take these two guys and I come back and see if I plug them in. So cosine of u is good, but I'm only left with d theta. So I need to solve for d theta over here. I get d theta is du over 7. So I plug in du over 7. Realize that over 7 just means it's multiplied by 1/7. Pull out a 1/7. I have the integral of cosine of u du. Again, now I'm done because that's an easy integral. The integral of cosine, what function if I take its derivative gives me cosine, is sine. So this is 1/7 sine of u plus c. Plug u back in, and I get 1/7 sine of 7 theta plus 3 plus c.